Hi, I welcome you all to this session where we are going to look at a common and basic application of the Schrodinger's wave equation. And that application is the particle which is entrapped in a one-dimensional potential box. And taking you along on this journey is Dr. Yunus Jerusha, an assistant professor of physics. You might have this question in your mind. This particle is bound within certain regions of space. If this particle is bound, can this particle still be described as a wave? Yes, it can be described as a standing wave. Let me tell you how. The particle which is inside the box keeps moving within the boundaries of the box. As it moves from one boundary to the other boundary, its energy changes. This particle at the first boundary will have maximum potential energy and will therefore be at rest. Once it starts moving from that boundary to the other boundary, its kinetic energy increases and is at its maximum at the center of the box. And therefore, it starts vibrating with a very high amplitude. As it proceeds to the other end of the box, its kinetic energy decreases and the potential energy starts to increase. Thus, at the two ends of the box, the potential energy is at its maximum, and at the center of the box, its kinetic energy is at its maximum. Therefore, there is a variation in the amplitude of the particle which is present inside the box, and we have a standing wave pattern. That is how the particle in a one-dimensional box can be said to have wave nature. Based on the wave-particle duality postulated by Louis de Broglie, a particle which is accelerated by high potentials moves with a very high velocity and possesses wave nature. And when the same particle is bound, it cannot move and therefore loses out on its wave nature and exhibits its original character, which is a particle. Therefore, a particle in motion has wave nature and a particle when it is at rest has particle nature. Let us consider a particle, in our case an electron, possessing a mass m and moving along the x-axis enclosed in a one-dimensional potential box as shown in the diagram. Since the walls are of infinite potential, the particles do not penetrate out from the box. Also, the particle is confined between the length A of the box and has elastic collisions with the walls. Therefore, the potential energy of the electron inside the box is constant and can be taken as zero for simplicity's sake. And outside the box and on the walls of the box, the potential energy V of the particle, that is the electron, is infinity. And inside the box, the potential energy V of the particle, the electron, is zero. We can therefore write the boundary conditions to be as follows. The potential energy of the particle is zero within the walls of the box, and the potential energy is infinity at the walls of the box and beyond the walls of the box. Also, since a particle cannot exist as a wave at the walls of the box and beyond the walls of the box, the wave function psi becomes zero. To find the wave function of the particle within the box of length A, we consider the Schrodinger's one-dimensional time-independent wave equation, which is d square psi by dx square plus 2m by h cross square into E minus V psi equal to 0. Since the potential energy inside the box is 0, that is V is equal to 0, the particle has kinetic energy alone and is therefore named as a free particle. And for a free particle, the Schrodinger's wave equation can be written as d square psi by dx square plus 2m E by h cross square psi equal to 0. This we call as equation 1. We now replace 2m E by h cross square with k square, and the Schrodinger's one-dimensional time-independent wave equation for a free particle becomes d square psi by dx square plus k square psi equal to 0. This we call as equation 2, where we've made the appropriate substitution for k square. Since equation 2 is a second order differential wave equation, it should have two arbitrary constants, and the general solution of this equation 2 is given by psi of x is equal to a sin kx plus b cos ax, which we represent as equation 4. And these two arbitrary constants a and b are determined by applying the boundary conditions which were just seen. The first boundary condition is at x equal to 0. There is no chance of finding the particle as a wave at the wall which is present at x equal to 0. Therefore, the wave function psi is equal to 0. We now substitute x equal to 0 and psi of x to be equal to 0 in equation 4. And equation 4 turns out to be 0 is equal to a sin 0 plus b cos 0, which is 0 plus b, which results in b to be equal to 0. This value of b is substituted in equation 4, and we have therefore psi of x to be equal to a sin kx, which we denote as equation 5. Now for the second boundary condition, which is at the second wall present at x equal to a. Here also the particle cannot be present as a wave since its potential energy is at its maximum, which is infinity. Therefore, the wave function psi is also equal to 0. We substitute these two values in equation 5. Therefore, 5 turns out to be 0 is equal to a sin ka, which we denote as equation 6. In equation 6, a cannot be made equal to 0 since the other arbitrary constant b is already 0. Therefore, sin ka alone can be made equal to 0. And we all know sin ka can be 0 only when ka takes integral multiples of pi. And when we say integral multiples of pi, n has to be a positive integer, which is 1, 2, 3 and so on, giving us k to be equal to n pi by a, which we represent as equation 7. Substituting the value of k in equation 5, we get the wave function associated with a particle which is confined in a one-dimensional potential box to be psi n of x is equal to a sin n pi by a x, which we represent as equation 8. Our first task here is to find the energy of the particle, and this energy has a name. We call it as the energy eigenvalue. This we obtain by squaring equation 7. On squaring, we have k square to be equal to n square pi square by a square, which we represent as equation 9. There is already another expression for k square in the form of equation 3, which is k square equal to 2me by h cross square. We now make a substitution for the reduced Planck's constant h cross as h by 2 pi, and in the denominator we have h square by 4 pi square. When 4 pi square is taken to the numerator, we have the numerator to be 8 pi square me by h square, which we represent as equation 10. Equating 9 and 10, we obtain n square pi square by a square equal to 8 pi square me by h square. On cancellation of pi square and a small rearrangement of these terms, we obtain the energy eigenvalue to be En is equal to n square h square by 8ma square, which we represent by equation 11. From equations 8 and 11, for each value of n, there is a wave function and a corresponding energy level. Thus, we can say that each value of En is known as the eigenvalue and the corresponding value of psi n is called as the eigenfunction. For various values of n, we get various energy values of the electron. The lowest energy value or the ground state energy value can be got by substituting n equal to 1 in equation 11, and the lowest energy or the ground state energy E1 is given by h square by 8ma square. In a similar way, we obtain the energies for the higher energy levels by substituting n to be equal to 2, 3, 4 and so on. We have therefore E2 to be equal to 4h square by 8ma square. On simplification, it is 2 square E1. Similarly, E3 is obtained as 3 square E1. E4 is obtained to be 4 square E1. In general, we can write the energy eigenvalues to be En is equal to n square E1. Therefore, it is found from the energy levels E1, E2, E3, etc. The energy levels which an electron has are discrete in nature. This is a great success which is achieved in quantum mechanics, since in classical mechanics the energy levels are said to be continuous. From the pictures which are shown here, it is seen that the energy levels are discrete in nature and higher order energy levels are closely spaced. Looking at the diagram to the right, it is observed that for every shell which an atom possesses, there is a distinct energy level. And exchange of energy among the electrons between different shells or different energy levels is discrete in nature. It is also observed that the lowest energy level or the ground state energy has a value of minus 13.6 eV and not 0 as was proposed in classical mechanics. With our first task of finding the energy eigenvalue complete, we set about with the second task, which is to obtain the eigenfunction. In order to obtain the eigenfunction, we need to determine the arbitrary constant A. And in order to find this A, we need to normalize the wave function. Normalization is the process by which the probability P of finding the particle inside the box can be done. The probability of finding the particle is given by integral 0 to a mod psi square dx equal to 1. 0 and a being the boundaries of the box within which we have the particle. Therefore, the probability is exactly equal to 1. From equation 8, we substitute for psi as a sine n pi by ax, and we have this equation which is integral 0 to a mod a sine n pi by ax the whole square dx equal to 1. Squaring it, we have inside the modulus a square sine square n pi by ax. We now replace sine square n pi by ax in terms of cos, and we have a square integral 0 to a 1 minus cos 2 n pi by ax by 2 dx equal to 1. We split the term which is within the parenthesis into two terms as a square by 2 integral 0 to a dx minus integral 0 to a cos 2 n pi by ax dx equal to 1. On integrating, we have the first term alone to be present. The second term disappears because the integral of cos gives us sine, and on substitution of the limits either 0 or a, we have the second term giving us 0. Therefore, we are just left out with the integration of the first term alone, giving us a square x by 2 with the limits 0 to a, and on substitution of the limits we have a square a by 2 to be equal to 1. Cross multiplying, we have a square to be equal to 2 by a. Taking the square root of a square, we have a to be equal to square root 2 by a, which we represent as equation 12. Substituting this equation 12 in equation 8, which is the wave function sin of x, we have the eigenfunction or the wave function for the particle in a one-dimensional box to be square root 2 by a sin n pi by a x, which we represent as equation 13. This equation 13, as was told, is the wave function of the particle which is enclosed or entrapped in a one-dimensional potential box. We now look at the normalized wave functions and the probability densities which are present for a particle in this one-dimensional box along with their energy levels. It is observed that the wave functions are sine functions which taper off at the boundaries. Similarly, the probability densities are real and positive and do not have any negative values. We now observe the various wave functions for higher values of n, and we are able to see that there is a variation of the wave function as the particle moves between the two boundaries at x equal to 0 and at x equal to a. In summary, the energy eigenvalue is given by En is equal to n square h square by 8m a square, where n takes integer values which are positive as 1, 2, 3 and so on. M stands for the mass of the particle which is present inside the box, and A stands for the dimension, or in our case the length of the box. There is another expression for the energy eigenvalue given by En is equal to n square E1, where E1 stands for the ground state energy or the lowest value of energy which the particle can take. Both these expressions very clearly prove that energy is discrete in nature for a particle which is in movement. We have the eigenfunction given by psi n of x is equal to square root 2 by a sine n pi by a x. Thank you for your patient listening.